All right, the rules of derivatives, chapter 3.3. All right, doing the limit definitions of derivatives was pretty miserable. It is a lot of algebra. It is pretty tough. It is definitely not something that we enjoy doing. All right, we have to do those limits. We have to either use a table or all that algebra to figure them out. It gets messy. It gets hard. So we learned a better way. And the more of those you did, I hope you kind of started to notice some patterns. All right, so the first thing, if you take the derivative, I said this at the end of my last video actually, if you take the derivative of a constant, it's always equal to 0. Okay, so that's our first rule. A horizontal line, y equals 5, for instance, the change in that horizontal line, vertical change of that horizontal line, is always 0. Okay. All right, and then the power rule. All right, we use this constantly. All right, the power rule just says, hey, if you have x to a power, okay, the derivative of that, all right, and so we've done this a few times, the derivative of something to a power, for instance, I think I still have my decimals from that last one. I can bring it back really easily, I hope, maybe. Oh, we did an absolute value, that's right, sorry, all the clicking. All right, this thing. All right, the derivative of a power, like an x cubed, we did a few of these. What we kind of figured out was that it was 3x squared. This part became this part. So you see the 3 kind of moved in front and we went down to its second power. That is exactly what we call the power rule. All right, if you're taking the derivative of something to a power, you just move the power to the front and reduce by 1. So the derivative of x to the 6th is 6x and then reduce by 1. So the derivative of x to the 99th is just 99x and reduce it by 1 to the 98th. All right, this only works with x to a power, okay? But things like the square root of x, we learned you can write as x to the 1/2. So we can do this. Move the power in front, 1/2 x, but then reduce by 1, so negative 1/2. Negative exponents, we learned about move to the bottom of a function, or a fraction, I should say. And so this is not 2 over, but 1 over 2 square root of x. All right, and we actually did this in that last notes. We did the derivative of the square root. Took a lot of work, but the power rule does it very easily. All right, and then the derivative of even weird fractions, as long as it's 1 on the top or a number, not another variable, you can just move it to the top, make its exponent negative, and do the power rule. So you move the power in front, negative 5x. Now to reduce negative 6 by 1, so negative 5 by 1, negative 5 minus 1 is negative 6. So here the negative number will stay on the top. Negative numbers don't move, negative exponents do. All right, and so that is our power rule. It makes doing derivatives extremely easy. All right, and we love to do that. All right, the sum, difference, constant, multiple rule. In general, usually we have these polynomials. We have a lot of these things being added. Basically, this rule just says, hey, you can do the derivative of each one individually and then just combine the pieces. And numbers in the front, yeah, it's a kind of, you're multiplying, so it's fine. So multiplying by constant. This thing, if I take its derivative, I multiply, I bring that 3 in front, so it would be 3 times 4, x to the reduced by 1 squared, plus 3 times 2. Sorry, I should write that the other way. Bring the exponent in front. 2 times 3x reduced by 1. Minus 5 versus x to the first, so 5 times 1 is minus 5. The derivative of a constant is 0. And then we reduce 12x squared plus 6x minus 5. We can do derivatives very, very quick and easy. Bring the exponent in front. 2 times 8 and reduce by 1. Derivative of a constant goes away. Negative 3 times 5x squared. Remember, bring this up. So negative, so it was plus, so minus 2 times 6x to the negative third. So 16x to the 7th. 15x squared minus 12 over x cubed. All right, so we can do these and we can start to do them very quick, very easy. The power rule makes this really nice. So this derivative, bring that in front. Negative 3 times 9, x to the negative 4, subtract 1. All right, 2/3 times 6. X to the, this is where it gets a little tough. 2/3 take away 1 is negative 1/3. 8 times negative 5. That's to the 7th. I'm running out of room, so we're going to come back up here. Remember, square roots are like 1/2 powers. So 1/2 times 6, that's negative 1/2. All right, so let's reduce. 1/2 times 6 is 3, but x to the negative 1/2 becomes divided by the square root of x. Remember, negative exponents move to the bottom, and the 1/2 power, the square root. Negative 3 times 9 would be minus 27. X to the negative 4th becomes positive 4 on the bottom. 2/3 times 6. 6 times 2 is 12. Divided by 3 is 4. X to the negative 1/3 becomes x on the bottom inside of a cube root. Negative 5 times 8, that's negative 40. And x to the 7th just stays. So the power rule, super, super useful. Can do a lot of derivatives for us. Definitely the most important rule we have for derivatives. We use it literally constantly. Okay, use it, use it, use it. But the power rule does not work if two things are being multiplied. Like, yes, 9 times this, that's multiplication, but 9 is just a constant. So the power rule only works for just constants being multiplied. And then all these additions or subtractions. If you have two things being multiplied, the power rule does not just work. You don't just do the derivative of these two things individually. Okay? So that is the limitation of the power rule. All right, so if you have two things multiplied, we have to use this thing called the product rule. All right, two different things multiplied, we use the product rule. Okay, you do not, I repeat, do not just get to do the derivative of each one individually. All right, the power rule says this. Not the power rule, the product rule says this. If I want the derivative of a product, all right, these two things multiplied together. Now, sometimes, yes, you could just distribute and you could take the derivative using the power rule. But if you can't just multiply them together, okay, sometimes we'll have, some very crazy things get multiplied. So we're learning this rule. The product rule says take the derivative of the first thing. So what's the derivative of this first thing? Well, 3 times 2, that's 6, x squared, times the second piece just left alone. You then add the first thing just left alone times the derivative of the second piece. So the derivative of the second piece, 3x minus 5, this is like x to the first. So we do 1 times 3, that's 3. Reduced by 1, x to the 0 just goes away, so we just have 3. And the derivative of minus 5 is 0. So the derivative of our second thing is just 3. All right, so the product rule, derivative of the first times the second thing left alone plus the first thing left alone times the derivative of the second. Okay. Now, usually it's just a little bit easier to simplify. This isn't too hard. 6x squared times 3x, 18x cubed, minus 30x squared, plus 6x cubed. These x cubes can combine. So that's what? 24x cubed minus 30x squared. So that's our derivative. Okay. So again, how we do a product rule. Now, if we had just, distributed and now done the power rule, 4 times 6 times x cubed, so 24x cubed minus 10 times 3x squared minus 30x squared. All right, so it becomes the same thing. But in general, that product rule, usually, depending on what we're doing, will help us out. Okay. So let's try it again. I have x here. We have two things multiplied together. We could distribute, all right, but that's going to be a very big distribute problem. So we try the product rule. The derivative of the first. So the first thing's derivative, 2x, 2 to the front, and then 2 minus 1 is 1, minus 3, and the derivative of 1 is just 1, times the second thing left alone, plus the first thing as it is, times the derivative of the second thing. 3 times 4 is 12 x squared, and the derivative of 5 is gone. All right, derivative of 5 is 0. All right, so now we can maybe distribute. Now we can try to work it out if we want to. Still having to do that, but at least it's a lot smaller. So 2x times 4x cubed would be what? 8x to the fourth minus 10x minus 12x cubed. Same thing over here. X cubed times 12x squared would be 12x to the fifth. 36x cubed plus 12x squared. Combine some like terms if we can. All right, so we have what? 12x to the fifth, 8x to the fourth, some cubes will combine. 12x squared and minus 10x. All right, so if you distributed all this, it would work out the same way. All right, but usually doing that product rule first just helps. All right, and again, technically these two things we could multiply together. This is x to the 1/2 times x to the negative fourth. You can add those two exponents. So that'd be what? 1/2 plus negative 4. So negative 4, that would be negative 8 halves plus 1/2, negative 7 halves. Its derivative would be what? Negative 7 halves moves to the front. And then we subtract 1 from that, so negative 9 halves. That is definitely not pretty. So that would be the derivative. We could, make this negative 7 over 2x to the 9 halves, so the square root of x to the 9th. So that's your answer. Or we can use the product rule. Okay, so the product rule says take the derivative of the first thing. Okay, derivative of the first thing would be 1/2 x to the negative 1/2 times the second thing left alone plus the first thing times the derivative of the second thing, so negative 4 over, so that would be x to the negative 5. All right, combining here, we'd have 1/2 x to the, let's see, that would be the negative 9/2 plus, I should say minus 4x to the 1/2 minus 5 would be negative 4/2. So that is what? 9/2. So 1 minus 4, that is negative 7/2. X to the negative 9/2. So the same answer, all right, as we expected, but once using the product rule and once trying to combine exponents. Now this one, you still had to combine those pretty much same exponents, but again, just getting an idea of what that product rule looks like. Okay, so again, the product rule. Derivative of the first times the second plus the first left alone times the derivative of the second. Okay, so that is your product rule. Now, with polynomials, sometimes just multiplying it out is definitely easier. But again, I'm not trying to just teach you how to do it with polynomials. The goal is to kind of be prepared for something in the future. So the product rule, derivative of the first times the second plus the first times the derivative of the second. All right, the quotient rule. All right, if you have two things divided, this thing is going to be pretty important. All right, the derivative of a quotient, something divided by something else, you take the derivative of the top times the second thing left alone, derivative of the bottom times the first left alone, so it kind of looks like a product rule, but instead of addition in the middle, you subtract. All right, and then you divide by the derivative, not the derivative, just the bottom thing squared. Okay, so let's try it. H prime here, the derivative of the top, okay, the derivative of 3x plus 4 is just 3 times the bottom left alone minus the derivative of the bottom times the top left alone over the bottom squared. Now we can try to simplify this a little bit. We can distribute 15x minus 15x will actually cancel out. And negative 20 and negative 3. So it won't always cancel out like that, but this one did. So we have our derivative. Okay. J of x here, we have something divided by something else, so that is our quotient rule. So J prime, the derivative of the top, derivative of 5x, 2 times 10x, times the bottom left alone, minus the derivative of the bottom, 3, times the top left alone, over the bottom squared. Simplify if you can. 10x times 3x, 30x squared, 10x times 4, 40x, minus 15x squared, 30x squared minus 15x, 15x squared, plus 40x. All right, and we are here. Usually these things aren't going to reduce very well. Usually nothing's going to cancel out. You can check to see if maybe this thing will factor. Well, then that goes in both things on the top, and 5. So taking out a 5x, we would be left with 3x plus 8. So no, not going to reduce. That is just our answer. That's our derivative. All right, so quotient rule again. The derivative of a quotient, we do the derivative of the top. So the derivative of our top thing, 2 times 3 is 6x, minus 4. Derivative of 2 is 0. times the bottom left alone minus the derivative of the bottom. 4 times 3 is 12, and reduced by 1, times the top left alone over the bottom squared. All right, the top can reduce a little bit. 18x to the 5th minus 12x to the 4th minus 36x to the 5th plus 48x to the 4th minus 24x cubed over the bottom 3 squared. Since there's no addition or subtraction in the bottom, we can do that. 9x to the 8th. All right, combine and split terms. The 5th powers, we got negative 18x to the 5th. The force, I've got negative 12 and 48. Sorry, my handwriting with this pen is a little tough sometimes. And minus 24x cubed all over 9x to the 8th. Technically, all those can get reduced by 3 and an x cubed. All right, 3x cubed goes into everything. So we can reduce everything by 3x cubed. So what? Negative 6x squared plus 12x minus 8 over 3x to the 5th. All right, so try to reduce these things if you can. All right, so this one did reduce. All right, and last but not least, we can do this with some graphs. All right, so if we have an f function and an h function, f and a g, and for number 130 here, we are adding our two functions together. So if I want the derivative of this addition, well, the derivative of an addition is just the derivative of both little pieces added together. So at 1, what is our derivative of f? Our derivative of f, what's the slope right here? Well, that's negative 1. So the derivative of f at negative 1, at 1 is negative 1. The derivative of g at negative 1, why am I saying negative 1? Derivative of g at positive 1 is 1. So our derivative of h overall, add those two things together. All right, h prime at 3. If you're adding these two things together, well, the derivative of f at 3 is constant, so 0. The derivative of g at 3 is undefined. All right, we can't do the derivative at a turning point like that, at a sharp corner. So overall, our derivative undefined. All right, our derivative at 4, if we're adding these two pieces together, we do f at 4, that's 0, plus g at 4, that's 1. So overall, our derivative there is 1. I hope we're okay there. All right, if we multiply though, if you multiply these answers, we have to do our product rule. All right, so the derivative at 1, the derivative at 1. So to do a product rule, remember it's f prime g plus fg prime. So for h prime at 1, all right, f prime, the derivative of f at 1 was negative 1 times just the g value at 1 is 1 plus f at 1 has a height of 3. G prime at 1, its slope is 1. So we then add these two things together. Negative 1 plus 3 is 2. All right. H prime at 3. Well, we already talked about how G prime at 3 was undefined. So we're going to skip that one. All right, h prime at 4. All right, so to do h prime, we do f prime at 4 was 0 times the value of g at 4 was 2 plus the derivative of this, the first thing. So f at 4 was like 2.5 times g prime at 4. That's 1. So 0 plus 2.5 is 2.5. All right, last but not least, a quotient rule. All right, f prime g minus g prime f over g squared. All right, so we're going to skip the third one. All right, but f prime at 1. Let's see. So, all right, our f prime at 1 was -1 times our g at 1 was 1 minus our g prime at 1 was 1 times our f at 1, that's 3, over g at 1 squared. All right, so we have -1 minus 3. That's -4 over 1. That's -4. All right, and h prime at 4. All right. H at 4. H prime at 4, I should say. So f prime at 4 was 0 times g at 4 was 2.5 minus g prime at 4. Oh gosh, I lied to you. F prime at 4. I think I said this one over here wrong. F prime at 4 is 1 times g at 4 is 2.5 minus g prime at 4, that's the 0, times f of 4, that's 2, over g at 4, that's 2.5 squared. All right, so we wind up with 2.5 over 2.5 squared. That is actually 1 over 2.5. All right, and so I'll leave you with this. If you watched this video to this point, that is fantastic. If you email me and you submit this answer, show your work for this thing, email that to me, a picture of your work on that one. I will give you some extra credit for the course. All right, so it's a hard problem. If we want to find this derivative, all right, so this is just algebra. It's a quotient rule. Okay, something divided by something, quotient rule. But when you do the derivative of the top, you've got to do a product rule. So that one's a fun problem. You have to do a product rule and a quotient rule in the same problem. All right, so again, that will be some extra credit. Do that one on paper, show all your work, and send that to me for some extra credit.